Hi students, in this lecture I am going to discuss angular momentum of a rigid body. After that, conservation of angular momentum. Let us see first one. Right. So if you remember in lecture 18, in question number 46, we have discussed that a point mass attached to a massless string and that point mass follows a subtler path. So calculate angular momentum about point P, about the center O, right? So this question we have solved in lecture 18, question number 46. Okay, let us see now the results what we got. If this is a theta and this is equal to R, and we have taken this as z axis. So this is X and this is Z and Y is into the both. If you take at this instant, so we are taking omega is now like this. At this instant, the velocity is now along positive x-axis. That means it is now moving into the board, right? See one's angular momentum at that instant. L bar equal to R bar cross P bar. In the place of R bar, see what we can write. R into sine theta I cap. Next, minus cos theta k cap. That is R bar, right? R bar cross P bar. P bar is M into V is now along positive axis into the board at this instant, okay? So it is Vj cap. See result what we got. This is we are taking about the point P, right? So you can take M, V, R, okay, outside. Remaining is I cap cross J cap. That is a K cap. So sine theta k cap cross j cap, that is minus I cap, minus of minus plus cos theta I cap. Okay. So here angular momentum is having two components. One is along z axis, so k cap, and one is along positive x axis. And we can see this component keep on changes. Okay, at this instant it has a component along positive x-axis. This will keep on changes. Now if you observe carefully, when we are taking about the point O, or do one thing, first take here component of this vector along z-axis, Lz, okay, that is mv r sine theta, mv r sine theta. In this diagram, r sine theta is nothing but radius of the circle, right? So MVR, this is now z component of angular momentum, or you can say component of angular momentum along the axis of rotation. So in the place of we can write R omega. It becomes now mr square omega. So it is now I omega. So in this case, what we are saying that direction of omega bar is along z axis, means along axis of rotation. But direction of L bar, it is not along z axis. That means in this case, we cannot write L bar equal to I omega bar. Okay. It is not equal to I omega bar because direction not match. But we can write Z component, or we can say component of L bar along Z axis, along the axis of rotation equal to I omega. Okay, so keep that point in mind. Now focus when we are taking about center of the circle, theta becomes 90, then cos 90, 0. Remaining is now L bar, that is equal to M into V into R, that is I omega. In this case, angular momentum is along Z axis. Okay, because this is now 0. When you are taking about O, that means angular momentum having only one component, that is along the axis of rotation. Omega also along same direction. That means in this case, we can write L bar equal to I omega bar. Okay. Let us now generalize this for a rigid body. That is, if we consider one more particle diametrically opposite. Okay. Consider one more particle diametrically opposite. See what happens. Having same sense of rotation, take diametrically opposite. Where change comes? Coming to R bar, this is R bar. Okay. Coming to Z component, no change, minus cos theta k cap, right? Z component. If you are taking like this R bar for this components, one is along negative x-axis and negative z-axis. Regarding z component, no change. This becomes minus I cap. Okay. One component comes like this along negative x-axis. So this is minus I cap. Next, coming to for this particle at this instant, velocity is now outwards, means out of the boat, means minus j cap. So here we get minus. So this is minus and this is minus. Minus minus becomes plus, means no change in this. Okay. But since we got minus here, this will become now minus I cap. Okay. That means for that what happens is about P, L value will be it is M V R sine theta k cap. In this component no change. The other component is now cos theta I cap. It is a minus. So when you are taking diametrically opposite, that means if you take sum of these two, then the net value about P. Okay. Net value about P, that will be, it is MVR sin theta k cap, again MVR sin theta k cap, right? That means it is only along Z axis. It is only along Z axis. See now how we are generalizing this, or you can say how we are extending this for rigid body. Suppose we are taking a uniform ring, okay, and take axis of rotation. Rotation is now about its own axis. Rotation is about its own axis. Means passing through center of mass normal to plane of the ring. If you are taking one point mass right of the axis, we can find diametrically one more point, right? Means left of this axis. If I am taking a point mass here, we can find diametrically one more point mass at same distance. Okay, like here, right? One point mass here. Diametrically here, one more point mass. In such a case, what happens is angular momentum will be only along the axis of rotation. So this we are saying as if body is symmetric about axis of rotation, if body is symmetric So in that case, we can write L bar is equal to I omega bar. If body is symmetric about axis of rotation, this is more important about axis of rotation. Its meaning is if you are finding one point mass on one side, we can find point mass on the other side also. The meaning of body symmetry. For example, if we consider same ring which is uniform, let us take axis is now tangent. Axis is now tangent. Okay. Now, even though body is uniform, it is not symmetric about axis of rotation. That means at this instant, if I am finding one point mass here, there is no point mass on the left of the axis. Get the point. There is no point mass on the left of the axis. So here body is not symmetric about axis of rotation. Students should be very careful here. One is uniform and one is symmetric. Both are not same. In both these cases, ring is uniform. But about this axis, body is symmetric. About this axis, body is not symmetric. When body is not symmetric, we cannot write L bar equal to I omega bar. So L bar not equal to I omega bar. But its a component along the axis of rotation is equal to I into omega. Okay. So same conclusion here. Right. And this conclusion here. Extension of that. Component I omega. Component I omega. Right? So in case of rigid body, if body is symmetric, we are taking this one. If body not symmetric, we take component along the axis. Okay. So this is regarding angular momentum of a rigid body. Right. Let us now focus conservation of angular momentum. Let us see now. So we have discussed net torque. And net torque is equal to the rate of change of angular momentum with respect to time. Okay. If net torque on a system, if net torque on a system is zero or 0 bar, that implies L bar is a constant because derivative 0 means this is a constant, right? So L bar is constant. Means angular momentum of the system is a constant if net torque on the system is constant. This is known as law of conservation of angular momentum. Okay. So first we have to focus on the system net torque 0 or not 0. Right. And here one more thing we have to keep in mind about which axis net torque 0. About the same axis we have to conserve angular momentum. For example, net torque not equal to 0, but Z component of net torque is 0. Okay, then we can say that L bar not a constant, but Z component of L bar is a constant. If you remember, while discussing conservation of momentum, we have discussed same thing. If net force 0, momentum of the system constant. If net force not 0, suppose x component of net force is 0, then we can write x component of momentum of the system is a constant. So exactly same logic. Okay. So statement is that if net torque on a system is 0, then its angular momentum is a constant. This is known as law of conservation of angular momentum. Okay, let us now focus on problems. That's the first one, a very simple question. Find the time period of rotation of the Earth if its radius becomes a half. In that condition is if mass is a constant, if density is a constant. So take time period of rotation of Earth as 24 hours. Let us see how to solve it. So we are taking now Earth as a solid sphere. We are focusing now time period of rotation. So we are knowing that time period of rotation is 24 hours and that is given. Now see condition, radius becomes half. So here no torque is acting on Earth, right? So net torque on Earth is 0. So we can write angular momentum of the system is constant. So I'm writing here I omega. I omega for Earth is a constant. It is constant. For I am writing here 2 by 5 mr square omega 2 pi by t. This is a constant. Here 2 by 5 is a constant. If mass is a constant, then 2 by 5 m is a constant. 2 pi is a constant. Therefore, t proportional to r square. Then we can write T2 by T1 is equal to R2 by R1 whole square. Now in this initial time period of rotation, 24 hours. So T2 by 24 hours is equal to, if radius becomes a half, R2 is R1 by 2. It is 1 by 4. Cross check once, okay? R1 by 2. R1 gets cancelled. 1 by 2 square. 1 by 4. 1 by 4. That implies T2 value how much? 24 by 4. 6 hours. That means Earth completes one rotation in 6 hours. Okay. Now consider second condition, that is density constant. See what happens. If density constant, in the place of mass, we can write it is a 2 by 5. In the place of mass, it is a 4 by 3 pi r cube dense volume into density into r square into r square, right? Volume into density, that is mass m r square into 2 pi by t is a constant. Now see what happens here. R cube r square r power 5. So t proportional to r power 5 because the remaining are constants. So now we can write T2 by T1, that is equal to R2 by R1 whole power 5. Okay. So T2 by 24 hours is equal to, it becomes 1 by 2 whole power 5, 1 by 32. That implies T2 equal to 24 by 32, 3 by 4. Right? 3 by 4 hours. That means 45 minutes. Means Earth completes one rotation in 45 minutes. Okay. Even you can see some questions like this is a North Pole, this is a North Pole, this is South Pole. If ice caps here, if they are melting, if ice is melting here, then water form, that water moves away from axis in all directions. That means Now, moment of inertia for Earth increases because water is moving away from axis in all directions. When I is increasing, omega will decrease. Omega decreasing means time period of rotation will decrease, right? Wait. I omega constant. When water is moving away from axis, I value is increased. When I increased means omega will decrease. Omega decreased means 2 pi by t. So t value is increased. Means Earth will take more time to complete one rotation. Okay. If polar ice caps melt, what happens to time period of rotation? That will increase. Okay. Because I value increased, omega has to decrease because I omega is a constant. Omega decreasing means 2 pi by t is decreasing, means t is increasing. Okay, let us see next problem. A diver having moment of inertia given 6 kg meter square. Diver means a person who is jumping into swimming pool, right? Jumping into water. Okay, a diver having moment of inertia 6 kg meter square about an axis through his center of mass rotates at an angular speed of 2 radian per second about that axis. If he folds his hands and legs to decrease the moment of inertia to 5 kg meter square, what will be the new angular speed? So you can focus I value given, omega given. Here I value given, we have to find omega value. Now see once very simple and direct question. Simply we can write I omega is a constant. Means I1 omega 1 is equal to I2 omega. Okay. Initial I value 6. Omega value 2. Finally I value 5. Omega value we have to calculate. So 12 by 5 means 2.4 radian per second. Means initially person was like this. Now he's bringing his hands and legs close to his body. Okay. So what happens is now more mass is closer to axis of rotation. That's why moment of inertia has reduced. Okay. See next one. And this question taken from H.C. VERMA. See once. A kid of mass capillum stands at the edge of a platform of radius capillary which can be freely rotated about its axis. The moment of inertia of the platform is I. The system is at rest when a friend throws a ball of mass modem and the kid catches it. If the velocity of the ball is v horizontally along the tangent to the edge of the platform, when it was caught by the kid, find the angular speed of the platform after the event. Okay. Now see how to calculate. So first make a diagram for the given data. Right. See what is given here. Platform kid of mass capillum. Kid of mass capillum standing on the edge of a platform of radius capillary. Radius capillary. A kid is standing on the edge, his mass capillum. The moment of inertia of the platform is I. The system is at rest. A friend throws a ball of mass smaller tangential. You can say, for example, the ball is now thrown here in this way along the tangent. Its mass is smaller, its velocity v. Now the kid is catching that ball. Find angular speed of the platform. Now first we have to focus what is a system. Here system is now platform, kid and the ball. This is now system. For this system, net torque is 0, right? Now see what we can say here. Initially angular momentum, that is m into v into r. See, we are conserving angular momentum about axis of rotation of the disk. Okay. Then distance equal to r. So m into v into r, initial value. Final value, when the boy is catching this, you can say I plus moment of inertia m plus m into r square. That is I value about axis of rotation into omega. This is equal to initial value mvr. From this we get omega value. Okay. So direct one and very simple one. See the next one. Suppose the platform of the previous problem is brought to rest with the ball in the hands of the kid standing on the rim. The kid throws the ball horizontally to his friend in a direction tangential to the rim with a speed v as seen by his friend. See meaning of this. As seen by his friend. Its meaning is this is in ground frame. Okay. Find the angular velocity with which platform will start rotating. Okay. Right. So initially ball was in the hands of the kid. Now he is throwing. Then see, initially ball was in the hands of the boy and system was at rest. That means initially L value 0, right? So final value also must be 0. Now the kid is throwing the ball along the tangent. Its velocity is v in ground frame. Okay. Its mass is m. When he throws the ball in this way, it will rotate anti-clockwise. So about this axis, because of translation of the ball, angular momentum will be clockwise, and for disk and kid, it is anti-clockwise, sum equal to 0. Okay. If we are taking anti-clockwise as a positive, then see what we can write. 0 equal to I plus mr square, moment of inertia of the platform plus k into omega. We have taken anti-clockwise as positive, right? Next, coming to mvr, that is negative, minus mvr, that is equal to 0. Then we get the value of omega, right? Let us see next one. Suppose the platform with the kid in the previous problem is rotating in anti-clockwise direction at an angular speed omega. The kid starts walking along the rim with a speed v relative to the platform, also in the anti-clockwise direction. Find a new angular speed of the platform. So now here the question is that platform is rotating anti-clockwise. Now kid starts walking again anti-clockwise with a speed v relative to the platform. Okay. relative to the platform. Let us see how to start the problem. Disk is now means platform. It is now rotating anti-clockwise, given omega. Now the boy walking, he also anti-clockwise with a velocity v relative to platform. So initial angular momentum. See what happens. Initially, boy was at rest with respect to platform. So I'm writing here I plus mr square into omega. That is angular momentum of the system. Let us take when boy starts walking, it becomes omega dash. Okay. Then see what we are writing. For the platform, it is I omega dash. This is for the platform. Now focus for the boy. For the boy, given v is velocity with respect to platform. Okay. That means in ground frame, his velocity will be v plus r omega dash. Right? In ground frame, his velocity becomes how much? V plus r omega dash. So it is now v plus r omega dash. M into v into r. So initial angular momentum. This is a final one. Let us solve for omega dash. Omega dash. This can be written as I plus mr square. I plus mr square. This m is a capital, right? Let me correct it. Capital. This is a capital. I plus mr square into omega dash plus m vr, right? From this, see what we can write. Omega dash equal to omega minus mvr upon I plus mr square, right? So main thing we have to identify what is a system. Here system is a platform plus boy, right? In the earlier problem, platform plus boy plus ball. Okay.